Well, hello, pre-calculus students and seekers of general truths. In this video and in this entire lesson, we will study something called the principle of mathematical induction, or abbreviated PMI. Okay. And I've written it up here, and let's parse through this a little bit. If a statement, or it's usually a formula, but any statement is true for n equals 1, n just being a variable placeholder, and the statement being true for n equals k leads to its truth for n equals k plus 1, then the statement is true for all n is greater than or equal to 1. All right, so this is quite a handful, quite a mouthful of words here to fully parse and appreciate. But let me give you a visual example. It's sort of like saying if the first domino is going to fall, and every domino knocks the next one down, then we can say that all the dominoes are going to fall. Okay, so if you have a chain reaction and there's a start to the chain reaction and every part in the chain leads to the next part occurring, then the chain reaction will occur for everything from beginning to end. And you can, in the notes, you can also see an example of this as well when we look at the proof for the Tower of Hanoi formula. All right, and just some clarifying terms here. This first, we should state this. This first, there's two conditions to the principle of mathematical induction. This first part here, it's called the base case, and this is called the inductive case. Okay, base case and inductive case. And it's helpful as well for us to maybe just engage with a particular problem. Okay, so I'm going to show you how to prove Gauss's problem. So remember, Gauss's problem is the sum of the first integers, 1 plus 2 plus 3 plus 4, all the way up to n. According to Gauss, it's going to be equal to n times n plus 1 over 2. And there's other ways to show this, but I'm using this one as a way to illustrate the principle of mathematical induction. So what we're going to show is that first, is it true ever? Is it true for the most simplest scenario? So in this, what I mean by this is the base case. That's when n is equal to 1. Well, on the left-hand side of the formula, we would just have the number 1. On the right-hand side of the formula, we have 1 times 1 plus 1 over 2, right, because we're substituting in 1 for n. And this also turns out to be 1. So we're good. The left-hand side and the right-hand side are equal to each other. All right, now for the trickier part, which is the inductive case. And the inductive case says that the inductive step, okay, the base step in the inductive step, says that if the statement is true for some value k, all right, so what that means is that we're assuming that the statement is true when n equals k, and we have to show that the statement is true for n equals k plus 1. In other words, that whenever the formula is true for 5, we can show that it must also be true for 6. And when the formula is true for 6, we can show that the formula must also be true for 7, and so on. But rather than doing that an infinite number of times, we can just use variables k and k plus 1. All right? So we want to show that this formula, that 1 plus 2 plus 3 plus 4 plus ... up to k, and then one more step up to k plus 1, will be equal to, substituting k plus 1 here in for n, k plus 1 times the quantity k plus 1 plus 1, all of this over 2. Okay? So we want to show that if this formula is true for n equals k, then it must also be true when n is equal to k plus 1. And I'll just put parentheses around this. It helps you to visualize it a little bit better. Okay, so let's start here with our left-hand side. Well, we already have this here. And the nice part about this is that we can use the inductive assumption. Okay, so we're using the inductive assumption. we know that all of this here up to k is equal to the formula that we're setting, that the claim is making. Right? So up to k, this must be equal to k times k plus 1, all of this over 2. And all that remains for us to do is to work out the details. Adding k plus 1 to it will in fact give us this formula here. So it's not too much work to do. We have k times k plus 1, and then we're going to multiply this term here by 2 just to get the common denominator. All right, so combine all of this together. It's k times k plus 1 plus 2 times k plus 1. All of this divided by 2. And rather than distributing and kind of getting this all messy, we can just take out a k plus 1 here. So we're going to factor out k plus 1. And what we're left with is k and 2. All of this over 2, which as you see is equal to the right hand side, k plus 1 times k plus 2, and that's the same as k plus 1 plus 1. So this is equal to the right hand side, and thus the proof is complete. Okay, and let's just review a little bit here what we have shown. Two things: that this formula that Gauss gives us to add the first list of a list of consecutive integers from 1 on to n, it is true when we use the most simple scenario, when n is equal to 1. And it is also true that if the statement was true for n equals k, let's say k was 50, we can show that it's equal for k equals 51. And if the statement was true for 100, then we can show that the statement is true for 101. So since it's true for 1, it's true for 2, it's true for 3, then it will be true for every number from 1 on to infinity. Okay? And this is a little bit unusual, but this is mathematically sound, and it is what we call the principle of mathematical induction.